I'm going to talk a little bit about designing the required Southern Ocean observing system for predicting climate change, robot floats, satellites, and supercomputers. And I know this is not as much fun for our folks who are boots on the ground, but let me show you what we're doing. Okay, so we've all seen this, right? The Keeling curve. It goes up, 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 which is causing major reorganizations both in our atmosphere, our ocean, and every system on the planet. And with that comes these incredible global atmospheric temperature anomalies. We're certainly experiencing it here. Last summer, our normal 100-degree days, and I'm sorry, it's in Fahrenheit, is 62 here in Tucson. Last summer, we broke our record of 98 days with 108 by 10 in 1 year. And it was a La Nina year, which is insane. I just point that out. It's completely nuts. So global warming is really ocean warming because 93% of that heat is going into the ocean. And we are getting a better and better look at this. And there are a lot of people here at this meeting that do a lot more on this ocean warming than I do. But I want to talk about the combined influence of the Southern Ocean on the global climate system and how we're observing it and how it's changing. So, and I just want to point out and this is definitely from the American perspective, even though I'm showing you Paris because we're back in, woohoo, into our the Paris agreements, of course. But it is the law of the land here in our biggest economy in the world type of place that the Clean Air Act here in the United States does cover carbon as a pollutant. I know most people are probably surprised to hear this, but in 2007, the Supreme Court ruled that the EPA is required to, the statute is unambiguous. The Clean Air Act's sweeping definition of air pollutant includes any air pollution agent or combination of blah, 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 blah. They agreed. And we are back into the Paris Agreement, but the ocean's playing a big role. Everybody says, oh, but it's just slow and kind of increasing. Ah, yes, let's look at this. So this is from the Global Carbon Project that does such a brilliant job. And this, again, is also from the Global Carbon Project and says, oh, 23% plus or minus. But we think that we can reduce the uncertainty in the ocean sink that can reduce the total uncertainty in the global constraint on the carbon budget. And I'll just pop back here for a second. Notice how small the uncertainties are in the atmosphere, how large they are in the ocean, almost as large as the ones for the terrestrial biosphere, which are massive, of course. So how can we reduce this ocean uncertainty? And I'll just point out there are some really excellent, important areas that are going to need to be addressed soon. Verifying the effectiveness of ocean-based carbon dioxide removal now that the whole world seems to be interested in actually looking at trying to remove carbon by ocean solutions. And being able to verify that, I think, is incredibly important. Otherwise, we end up with greenwashing, a whole lot of money spent and no results. So let's look at this. This ocean carbon uptake, and this is where we get to the Southern Ocean, right? The upwelling. Where does it happen? What's driving it? How do we monitor it? This is what I would like to do. This is a NASA visualization by Shira et al. It's the air-sea carbon flux with the wind vectors over it. Now, this is not fully interactive, simulated, but it's beautiful, and it gives an idea of where we would like to be. We would like to go from near real-time to near real-time monitoring of carbon fluxes the same way we do for the atmosphere. But that's a massive task given that 72% of the Earth's surface is ocean, and we're not everywhere out in the ocean the way we are on land. So the role of the Southern Ocean in the global climate system is 67 to 98% of the excess heat, half of the annual oceanic uptake of carbon, and 3/4 of the vertical exchange that supply nutrients to the global ocean. Now, I'm sure most of you know that about SOCOM, the Southern Ocean Carbon and Climate Observations and Modeling Project. I'm the lead for the modeling. Jorge Sarmiento is the lead for the whole project. Lynn Talley, my dear friend, is the lead for the observations, with Ken Johnson and Steve Reiser. So this is an incredible project that now has pH sensors, carbon-related pH sensors on all of these floats. And can you believe it? We went from 0 to 200 floats basically in 6 years. And that project has been continued. We're deploying an additional 200 floats over the next few years, pandemic allowing. And we've been calculating air-sea carbon flux from floats for some time now. This is Alison Gray's amazing paper from 2018 and GRL. But what we're seeing is here are from ships and floats. Remember, these floats work under the ice. They work all year round. They give us measurements beamed back by Iridium satellite every 10 days. We get a profile back just like the main Argo system. And you can see here is that deep ocean old carbon coming up to the surface. And you can see the darker blue here, which would be our the invasion of the newer carbon and the spiraling upwards. This is Veronica Tamsin's great work. And over here, you can see some in-prep work where blue is that uptake, the anthropogenic carbon uptake, into the ocean. But red is this red over here. It's that outgassing. And it's driven by the upwelling of Southern Ocean waters. It's a big deal. So we're looking at this in more detail, both from the direct observations and from a biogeochemical Southern Ocean state estimate done by Matt Masloff, Arian Verity, who are amazing. We're also looking at it in SOMIP, the Southern Ocean Model Intercomparison Project, which is water stress, if you're looking for it under FAFMIP at the IPCC, at the CMIP archives. So please run them. And if you're not running them, come look at them. They're really cool. What if we were underestimating our winds and we increased the winds over the Southern Ocean? What if we, and this is common among models, climate models, to underestimate these winds. What if we had, we didn't include the freshwater forcing from Antarctica, and they don't do that either. What if we combine these two? So those are those three experiments. So I of course know that all of my ice sheet colleagues will be like, yeah, duh, we should totally have this. But this is the only scenario. So there are preliminary results that are already out on the importance of this wind and meltwater for observed chemical and physical changes by Ben Bronslayer, my brilliant postdoc, who's now off onto new adventures. And he had incredible impacts on not just the heat, not just the carbon, not just the freshwater, not just reproducing the observed observations, but also in what the future might look like for nutrient trapping around the Southern Ocean. And my student, Becky Beedling, who's now at GFDL, she's done some amazing work with CMIP6, looking at just how big the spread is in the cumulative carbon uptake over time due to just the Southern Ocean uptake. And it's enormous. It's over 100 petagrams of carbon, and that 100 petagram carbon is basically the net atmospheric change of about 52 parts per million in 2100. This isn't small. Getting our poles right is because they play such an outsized role in these carbon driving pollutants. They are crucial to get right in the future. So what I want to talk to you, and I know I only I'm doing all right here on time. I want to make sure I get from SOCOM our in the water floats to satellites and the way that we measure winds from satellites. And instead of just looking at the spatial coverage, I want to think about temporal. Are we undersampling the very large storms that we know exist in the Southern Ocean and any changes that might be occurring due to time? So we've got the Southern Ocean is now the most carbon observed ocean in the world because we have this deployment. And yes, big shout out to BGC Argo, Go BGC, which is Ken Johnson's led this mid-scale infrastructure project for the United States, funded by the National Science Foundation, and they have funding for 500 more floats to do the rest of the world. But I'm going to focus on the Southern Ocean because it's my favorite and because that's where we have all the measurements already. So let's talk about growing winds. Let's talk about what happens to an ocean if you blow more air over it. Not a joke. Okay, so this is where we want to go, and everybody can see all these lovely wind vectors and the impact it has on the fluxes if this were real. And here is where, this is the frequency of Southern Ocean storms, and I just wanted to show you, these are seasons, right? A, B, C, D, 4 seasons. They're bad. They're bad all the time. Now, unfortunately, they're not as bad in the Drake Passage where we have a lot more measurements than we generally do temporally than anywhere else. However, let's get down to this. I also am just a huge fan of Joellen et al.'s new paper in GRL showing the historical and projected changes in the Southern Hemisphere westerlies. So moving poleward as they have been, and moving and increasing in intensity. And we know a lot about why. This is from that fantastic Thompson et al. Paper, forcing with ozone depleting substances that's been, our ozone hole made the stratosphere very cold over the South Pole, 7 to 8 degrees colder than it was 50 years ago. That's a lot in Kelvin. And then, of course, the 1 to 1.5 degree warming in the troposphere. But that forcing from the greenhouse gases actually over time with our increased greenhouse gases is actually taking over. So we don't see a relaxing of those winds. Well, what about the evidence? So here is the altimeter derived surface wind speed increase from 1985 to 2018. It's all red because it's all increasing. You see a few little blue dots out here by Indonesia, a little in the tropical Pacific, but basically increasing. If you looked at the spatial mean annual wave power, and this is from Rivera et al., you see all these increasing down here, but it's kind of modest. But then you look at the Southern Ocean, and that's the red line. Yes, up, up, up she goes. So let's look at other ways of measuring what the impact of those winds on the ocean might be. Deep reaching is acceleration of global mean ocean circulation. Xi Jianhu, and the big global changes in wind speed and wind work. That's what we're seeing. You can see this, and you notice down here in this, it was in Science Advances here in 2020, the big red there. And these increases, of course, especially over the last 20 years. So gyro shifting poleward and increasing strength. And the summertime increases, I know, the IPCC and Harberton Bears tell us that we should see polar stratification, right? Antarctic stratification is not happening. This is the summertime increase in upper ocean stratification and mixed layer depth. Notice I've used the word increase. Where you see blue, it's a deepening of the summer mixed layer, according to J.B. Sally's amazing new paper in GRL. Check it out, 1970 to 2018 trends. So this Southern Ocean is a critical and precarious carbon cycling engine due to these changes. We had these strong winds pushing surface water north. The deeper water that rose to take its replace was absorbing carbon, basically from these upper mid-depth waters, intermediate water levels. But if it digs deeper to those deeper Pacific deep water, upper circumpolar deep water levels in greater magnitude, we basically increase the number of those red dots that I was showing you from the SOCOM floats. We increase the outgassing. That cuts the ocean sink significantly and potentially leads to our having to be even more aggressive at reducing our emissions to avoid heat catastrophes on land. So we did a neat paper with a bunch of my very favorite people, including David Long, who is our sort of godfather of surface vector wind scatterometry here in the United States. And we use the Southern Ocean State Estimate, and Matt Maslow was kind enough to collaborate and run these things for us. So what I want to show you is the high winds are of outsized importance to the carbon flux. They are much bigger because it's nonlinear as you get to higher wind speeds. We've known this since, Wanenkoff et al. And he has a new update, 2019. Everybody should check it out because he basically makes the high wind speeds even more nonlinear gas transfers. And what I want to point out is that what we get right now, and this is the ASCAT satellites, there's two of them, and they are very close together, and those are the red lines here. The yellow lines are a proposed satellite. We put in a proposal last year, in March this year. It's a pandemic, my brain, called Zephyr, Southern Ocean Storm Zephyr, because temporally, too many of the current set of scatterometers are measuring the same place at the same time. Now, there are good reasons to do that. Overlap allows you to calibrate and validate very, very well. And each country that's chosen to put up a surface vector wind scatterometer has chosen the same orbit, on purpose in order to be able to calibrate and validate. And that is incredibly valuable. But what it means is that we're only getting basically 2 independent measurements per day of the surface wind speeds. You know how fast those storms move. You know how large they are. And imagine measuring a hurricane twice a day for their wind speeds. Would that be adequate to characterize the peak winds and their movement and the force that they're applying? I would argue, and I think NOAA has argued, no, that's not enough. That's why we have P3 hurricane hunters that fly through them, et cetera, to get better real-time looks at what those winds are doing. So what we did was we did an observing system design experiment, basically ran this subsampled BSOSI with our full, all of the BGC Argo floats assimilated to actually look at how much carbon flux we were capturing by looking at these winds just twice a day, and then adding one more satellite orthogonally deployed, basically at 6-hour intervals instead of 12-hour intervals, you know, and just to see. And if you notice over here, the red and the blue dots, the red is ASCAT and the blue is what we would get with Zephyr. And you just notice you're subsampling a sine curve. The more temporal samples you have, and I know my paleoclimate people understand this, the more temporal sampling you have, the better you're able to do at capturing the peaks and the lows. So the problem is, so we added 20% wind to our BSOSI simulation just to see, like with SOMIP, what would happen if we added the additional wind we think we're missing. Okay, the sign flipped, right, from sink to source with 20% increase in the winds. We ended up, all that red is that outgassing. I'm very, I hope we don't have 20% increase because that would be incredibly scary. And then we sampled it just like we did before to see how much of the carbon we could see. ASCAT, under what we currently think the winds are, our normal run, got us about 81% of the carbon. Under the 20% increase, because of the nonlinearity, we only got 71%. If you add the orthogonal satellite, it doesn't matter. In today's climate, you get 96%. In a 20% increase, you get 96%. We need more sampling. We are undersampling the winds in the Southern Ocean, and it has a significant impact on our estimates of the carbon flux, even with the new carbon floats out, you know, carbon enhanced floats. So we've proposed SOS Zephyr to capture the Southern Ocean high winds to reduce the uncertainty in the global carbon budget by reducing the uncertainty in the Southern Ocean budget. And it's Nikki Lewandowski is my deputy PI. I'm the PI. I'd be launched from, and my collaborators, Ball Aerospace. And we'll find out in November if NASA's decided to fund us as part of their Earth Venture mission capacity. This would, I think, solve one of the great uncertainties, the great problems with going to this more real-time estimates of what the carbon fluxes go. It is wonderful to have BGC Argo and the ocean boots on the ground and more ships, more sail drones, more floats, more gliders are really essential to getting this right. But we are also just a little shy of what we need to do the atmosphere right, to do those surface vector winds correctly. And so we've made incredible progress towards near real-time carbon accounting. 15 years ago, we didn't have a Supreme Court ruling. We didn't have an international political agreement. We didn't have carbon-observing satellites or system model prediction or these carbon-sensitive floats. We have all the pieces. I, of course, am really betting on the Biden administration here. They proposed a record $6.9 billion budget for NOAA. I am still crossing my fingers. They're under budget negotiations right now. If they put that $1.4 billion extra boost to the NOAA budget, or NASA decides to give us our Zephyr satellite or some combination, we could actually move to our near real-time accounting, and our polar regions and our oceanography would finally play the real-time role in not just weather, but climate that I think we need to be doing. So this is my conclusions. What comes next? We're going to continue to build out our carbon observing and prediction system. We're going to complete implementation of near real-time carbon accounting. We're going to help publish the top 10 economies monthly carbon bill and hopefully save the planet, or at least the humans, because it's getting pretty hot here in Arizona. But thank you for having me. Hey.